Today we're just going to do section 5.2. It'll probably be like 35-ish minutes. I don't want to go bulldozing ahead when a third of the class is gone or whatever. So we'll do a little bit. Does anybody have, before we get started on that though, does anyone have questions from the 5.1 homework? I think it was 1 through 16 or so. Okay. So here's the deal with section 5.2. It's basically kind of the same idea as what we did in section 5.1, where we looked at these two-step story problems where you have to write the model and then solve the equation. And in section 5.1, if you had to write the model, you were always given 2 points and you had to build the exponential function out of it, right? What we're going to look at in 5.2 is a framework that we can use where we're not given specifically 2 points for the exponential function to build the equation, but different information which we can use to build our exponential equation. So it's still the same idea as what we looked at before. We're just going to introduce a framework that we can use to kind of do that equation construction. Okay? So the model or the framework that we're going to be using is this exponential population model. Now, I know it says population in it, and you think of, when we say population, you think of people or animals or something like this. Population doesn't necessarily have to be a living thing. It doesn't have to be a thing at all. It could be how an idea spreads or something. The population is a very vague term. It doesn't necessarily, we don't necessarily mean it has to be a living organism to use this. Everybody okay with that? Okay. So our population model says that our P is changing at a constant percentage rate R for every T units of time and then the model can be given by the equation yada yada yada, where the P naught is that initial population. So if you squint real hard at this model, you're going to see that it's really just that A times B to the X, where this whole piece is just our B then, right? Everybody okay there? Now, since this is a population model, I know that P naught always has to be a positive value, right? So let's think about what values of R would result in a growth or decay function. So I remember if the leading coefficient is positive, if that B value is greater than 1, that would mean we'd have exponential growth, right? So I notice that if R is greater than 0, 1 plus R over 100 is going to be greater than 0, because you're just adding a positive value to 1, which would imply that this is growth, right? And if that R value is negative, then our B value would be stuck between 0 and 1, which would tell me this is decay. Everybody feel okay with that idea? And I guess before we move on, I should mention one thing about this R. So R is given as a percentage. That's why we're dividing it by 100 in the formula. So if you wanted to convert that percentage to a decimal by hand or just in your head or whatever by moving the decimal point, you don't need to divide by the 100. Okay? That dividing by 100 is there because we're writing down our value of R as a percentage. Everybody feel okay there? All right, so let's look at a couple of examples. And we're just, for this one, we're just going to kind of try to decide whether these are growth or decay, and then what would the corresponding value for R be that would match up with them. So if I look at the first one, there's my value of B, right? Since that's greater than 1, I know immediately we're talking about growth. And to solve that value for R, well, I know that our B has to equal 1 plus R over 100. So 3.084 equals 1 plus R over 100. So to solve that equation now for R, what would we do? We're talking about this equation here. If I wanted to solve that for R, how would I do that? Okay, and how would I get everything, get the R or everything else onto one side, get the R by itself? Subtract by 1 and multiply by 100, right? When I do that, I get 3.84. And again, like if I wanted to, I could identify that as, instead of looking at the B in the beginning, I could use the R at the end, all of which, to tell it was growth. If I didn't look at the B at the beginning, it's fine. I don't have to do that. I could just look at the R at the end, and that would tell me growth also. We feel okay there? So if I look at the next one, I see that the B is between 0 and 1. So that's decay. So I can, to solve for my R, I can just set B equal to 1 plus R over 100. And just solve for R again. Subtract 1 and multiply by 100. So there I get negative 1.33%. Which again, if I wanted to, I could have just waited till the end after I solved for my R to decide it's decay because R is negative. That would have been an acceptable method as well. How do you guys feel on this? No problemo? Okay. The one catch on this is going to be the T, and how are we going to kind of write that, because that can change depending on the context of the question, how you want to format your model. So let's look at a couple of examples here. So determine the population model with an initial value of 15, increasing at a constant rate of 6% every year. So we're going to be writing a population model. It tells me that in the problem. So I'm going to just kind of be filling in my values for this. So I see the P naught, I remember, is the initial value. So I have that. I have the R is 6%. Do I know if the R is positive or negative? Positive. How did I know positive? What word in there is telling me it's positive? Increasing. And then it seems to me that T we're going to be representing as years, right? So if I do that, we'll just say P of T equals 15 times 1 plus 6 over 100 to the T. Bless you. Bless you. Oh my goodness. We need a priest. It's too much blessings for a layperson. Ha 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 ha. A layperson. So there we go. Everybody feel okay there? Let's look at the next one. It says determine the population model with an initial value of 15, increasing at a constant rate of 6% every 6 months. So notice that everything on this reads the same, except for the interval, right? So I could start and just kind of set it up the same way. But if I do that, then T is 6-month intervals, right? That's kind of stinky, because when I get done, if I had to solve for T, I'd have to remember to like divide it by 2 to turn it into years, or multiply it by 6 to turn it into months. What I'd probably rather have is to be able to write my model in terms of years or months. So if I did this in 1-year intervals, how many 6-month intervals are in a 1-year interval? 2, right? So my exponent here should be 2t, because I have 2 6-month intervals in every year. Does that feel okay there? Or maybe if I wanted to write it in months, how much of my 6-month interval is 1 month? 1/6, right? So my exponent here should be t over 6. Now, all of these will give us the correct answer. It's just about what unit do you want to have at the end, right? If it's not specific, and we can write as like, okay, it's 8.7 6-month intervals. Okay, that's a weird way of answering a question, but it's not wrong. But if it asks for how many months or how many years, you may want to write your model in a way where the unit conversion is already kind of done for you. You don't have to take your answer and convert it at the end. And we'll do an example here on the next one where we actually have to solve this, and I'll solve it with a couple of different models and show how we have to like manipulate things to get to the same answer. Everybody okay? So the next one says, suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it will take for there to be 400,000 bacteria. So just like in the last section, this is going to be like a 2-step problem where I'm going to Step 1, I'm going to write my equation, and step 2 is I'm going to solve it. So when I read this equation, I see that my P naught is 120. My T seems to be probably going to want to write that in hours. Probably makes the most sense. But I don't seem to be seeing an R here. There's no number for R on here. Is there something hidden in words that is telling me the R? What? Doubles. Yeah, that is what's telling me my R. What percent is doubles? 2 is wrong. 100 is correct. So for example, if you had $100 and you made 100% profit, you would have made an additional $100, giving us a total of $200. Hence, your money has doubled. So 100% change is equivalent to doubling. Everybody's okay with that? All right, so we have that then. And I think the natural thing would be to write T as 1 hour intervals. So how many 1 hour intervals are in our doubling period? Anybody? 3, right? I need 3 1 hour intervals to get 1 doubling. You guys agree? That's what you read. So it should be 3t as my exponent. Sound good? So that's like my step 1. Now for step 2, I'm just going to plug the 400,000 into P of t and solve for t. I'm just going to make that 1 plus 100 over 100 is 2. There's the 2 for the doubling also. So that's the equation I'm going to solve. Still don't have the algebraic tools to do that yet. We will, but not yet. So we're just going to take it to our calculator and plug her in. So there's my stuff into my calculator. Everybody feel okay with what I typed in? I'm going to set a window now. So remember, our T is representing time in hours. So after 3 hours, I've gone from 120 to 240. In 6 hours, I've gone from like 240 to 480. In 9 hours, I've gone from 480 to 960. So it's going to be a while, right? So I'm going to make maybe that X max out to say 100. It's probably good. Everybody okay there? And then my Y, well, my Y min, the least amount of bacteria I'll ever have is that initial 120. I'm not typing 120, and I'm good with just 0. That's close enough. And then my max has to be at least 400,000. I'm going to make it 500,000 just so I can make sure I can definitely see if the thing crosses or not. Everybody feel okay with what I typed in for my window? So I'll hit graph. Whoa! Did I goof something there? Oh. Oh my gosh. Yes, of course I did. Look, I'm so dumb. I'm so dumb. What's the mistake? It's the 3t, right? How much of the 3-hour period is 1 hour? 1/3, yeah. So it should be t over 3. Ay caramba.
We just got flashbacks from the joke Nick told us like 4 times. Yeah.
Was it about Bart Simpson?
No. It was like, so like he was out with his friend bowling and his friend was like, oh,
I've heard this joke
did he tell you the joke?
about the spilled beverage.
Oh my gosh, yes. Beverage.
You like how I censored that for school appropriateness?
I that joke like that was today like 3 times this year, like 7 Today was the only day it was funny. He's been saying it for a couple days. I don't know what today was. So when you said Columbo, we're like, we like looked at each other. Yeah.
I see. So I got, when I graphed on the calculator and found the intersection, I got 35.1 hours. Now, had I just done this as this, where t is going to equal 3-hour intervals, so if I do that on my calculator, and I solve this, I get 11.7. So if we wanted that answer then in hours, I can just take 11.7 and multiply it by 3, and I'm going to get that 35.1 back again. So it doesn't matter kind of how you do it, but you do have to be careful about like what unit is your t in. Is it in the same interval as your percentage change is written as? That's fine. If you do that, though, you're going to have to convert it to like a standard time unit at the end. Or you can change your exponent so it matches up with a standard time unit so that your answer is your answer. It doesn't matter to me which way you do it, but you have to be careful about kind of how you're going about doing that so that the units work out. Does everybody feel okay with what we've done here and the point of kind of showing you what's happening 2 different ways? Another very common presentation of an exponential situation is called radioactive decay. Those of you that have taken a chemistry course or maybe even an earth science course have probably talked about radioactive decay. So the idea is you have a radioactive substance. Slowly over time, that radioactive substance like ejects some part of it and changes into a new substance that's less radioactive or not radioactive at all. At the very end, it's something not radioactive at all, but it might take 2 or 3 stages to get there. Now, as chemists, the way we measure how radioactive a substance is, we measure the amount of time it takes for half of a sample to change into something else. Okay? That's called a half-life. So that's just the amount of time it takes for like half of your radioactive substance to basically become non-radioactive. If you think about it like the simplest situation where you've just gone from like uranium to lead, where you've changed into something not radioactive at all. It's a fairly canonical example. So here, if we're talking about a half-life, what is our value for R? Right, we still can use this model but what's R gonna be? So 50% is close, but it's not correct. Let me give you a hint. If this is radioactive decay, the R needs to be negative 50, right? We need to be an exponential decay. So 50% is like half off. That's great, but we need to make sure we write it as negative 50%. Everybody okay there? And then the way I would change my T is simply use the time it takes. So I'd use that half-life number. As my denominator, and that ought to do it. So that's just going to be kind of my general format for a half-life problem. Now, every model will be a little different because of the half-life, or the length of the half-life, but the setups are all going to be identical. They're still just one of these population models. It just, the R is negative 50 every time. So let's do an example here to kind of hammer this home. It says, suppose the half-life of a certain radioactive substance is 35 days. And you have 10 grams of the substance initially. Find the time it would take for only 1 gram to remain. So my initial amount, 10. Half-life tells me the R is negative 50. And the T I'm going to measure in days. So I know that 1 day is 1/35 of our half-life. So T should be T over 35. Everybody okay with the setup there? And that's step 1. So step 2 then is just solve that equation equal to 1. So again, that's calculator time. Everybody good with how I got that into my calculator? Notice I did 0.5 instead of 1/2 just because I don't have to muck around with a bunch of parentheses in my calculator. Just reduces the amount of buttons I have to press. If you did use the fractional, you'd have to make sure you put a parenthesis around the whole fraction before you do the exponent. Okay. Everybody good? Let's set a window now. So we'll start with 0, right? Now after 35 days, I'm going to go from 10 to 5. 70 days, I'm going to go from 5 to 2.5. 105 days, we'll go from 2.5 to 1.25. And then from to 105 or 140 days, we'll definitely be under 1 gram, right? So I'm going to use that 140 as the upper bound for my x, because I know somewhere between 105 and 140, we're hitting 1. Does everybody feel okay there? Now, the y's are really easy. What's the least amount of radioactive substance I'll end up with? 0, right? Eventually, it'll all go away. What's the most I'll ever have? The 10 at the start. So that's really easy. So I'm ready to go. There's my radioactive decay curve. There's 1. Just find the intersection. Second trace. Intersect command. Enter, enter, enter. And I get 116.3 days. What do you guys feel on that? NBD, right? Basically the same thing as yesterday or last time. We're just adding a new way of building that equation at the start, right? So that should feel pretty familiar. The last example says you start a bunny petting zoo. What a cute idea. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. How many bunnies do you have initially? Does anybody recognize that type of equation for my B of t? What do you guys notice that is? That is a logistic, right? We talked about those at the end of the last lesson. Go ahead. Okay. And that'll come in play later. So how many bunnies do we have initially? What time is initially representing? What time would initial be? What time do we mean when we say initially? Mm-hmm. What number should t be? 0. Yep, initially it's just t equals 0. So we're just doing b of 0. And what's e to the 0 equal? 1. So I'm left with 800 over 100, 99 plus 1. So I have 8 cute little bunnies at the start of my petting zoo endeavor. Part B says, what is the maximum sustainable population for your farm? Well, remember, logistic functions have 2 horizontal asymptotes, one at 0 and the other at C, where C is just the numerator. So that's it for part B. Just recognizing that it was logistic was all I needed there. My farm apparently can support 800 bunnies. That's crazy. That's a lot of bunnies. And then it says, how long will it take you to have 500 bunnies? Well, all I'm doing then is just taking my B of t, setting it to equal to 500, and then solving. We lack the algebraic tools at our current state to solve this by hand. So what are we doing? Into the calculator she goes. Okie doke, artichoke. So I'm going to use the fraction command so I don't have to muck around with like a million parentheses on this thing. I'd suggest you do the same. So there's my setup on my calc. Right, just copying down the equation that was given to me and then typing in 500. What's up, Maria?
Did you do the bottom?
So I pressed alpha and then y equals. That gives me the option to pick the horizontal fraction bar.
Yes.
So I just copied in. I'm just copying this model that was given to me in the problem. Okay. All right, let's pick a window now. Boy, I don't know how long this thing is going to take to like get an incredible population, but let's assume it's like a normal business and maybe it operates for like 25 or 30 years before it kind of like the person running it's like ready to sell and get out of business or something. I don't know. Feels reasonable to me. For the y's, though, I know what the y's are going to be. My y min and y max are going to just be my horizontal asymptotes. So 0 and 800. So I'll just type that stuff in and then hit graph and take a look and see what I got. So here's my logistic curve. Oh boy, those bunnies are really reproducing. There's my intersection. So second trace. Intersect command, enter, enter, enter. And I have about 10.2 years. What do you guys think on this? I think by year 10, I'm giving a bunny to everybody that comes and visits. Take one home. I have too many of these things. They're eating me out of house and home. All right. Well, that's it for today. That's the idea. At this point, you guys should be able to do like 17 to 32. Let me double check that those are, I meant 36. That's going to be due not this Friday, but the following. So the only thing due this Friday is 1 through 16. Or I'm sorry, Sunday. The only thing due this Sunday is 1 through 16. The following Sunday will be the 17 to 36, and then whatever we might add next week. Everybody feel okay? Again, we're just kind of dragging our feet a little bit for the people on Kairos. Don't want to stack too much up on them while they're gone. Little bit is okay, but like I don't need to do multiple 80-minute lessons and have you be like scrambling to catch up on. Plus everybody seems a little worn out, at least this week. And that's it for me. Everybody feel okay? You can spend the last 40 minutes or so getting started on the homework or just kind of wasting it, I guess, if that's your pleasure. You know.